gentlemen, and a very warm welcome, whether you're here in the hall in person or you're online. My name is David Tennant, and I'm a trustee of the Frank Jackson Foundation, and we are very proud to be funding the Gresham Professor of the Environment at this remarkable institution, which has been providing free public lectures of the very highest quality since 1597. If I could start with a couple of housekeeping announcements. Please note the emergency exits, which are on either side of the hall, and in the very unlikely event of an emergency, staff will guide us out through the doors to a meeting point outside. And as you probably know, this evening's lecture will be followed by a short question and answer session. If you're in the hall, probably the best thing to do is just indicate that you'd like the microphone to come in your direction, or if you're watching online, you can submit your questions by scanning the QR code, which should be on your screen. So on to the lecture. It's a great pleasure to introduce Professor Helen Czerski to you this evening. Helen has had a glittering academic career as a physicist, oceanographer, and broadcaster, and amongst her many awards, she holds the Institute of Physics Gold Medal for her ability to communicate and explain physics. So who better to tell us this evening about the ground we stand on? Ladies and gentlemen, Professor Helen Czerski.
Thank you. Thank you, David, and thank you for joining us here this evening. I want to talk about something that is hiding in plain sight. We walk about on it every day. We are creatures of the land, but we don't often think about what's happening underneath our feet. And what I want to do in this lecture is convince you by dotting around a huge range of sort of different perspectives on what the ground is. I want to convince you that it's more than just the stuff we stand on, right? It's more than just a foundation for our world, which is how we normally think of it. But it is actually a part of our world. It matters. And so I want to start with one of the most brilliant scientists in history at looking at the very basic and seeing the great stories behind it, and that is Charles Darwin. Now, of course, you will know Charles Darwin as the co-originator of The Origin of Species, along with Alfred Russel Wallace. Darwin got there first, but didn't publish. Terrible idea if you want to establish primacy in an idea. And he is, of course, known for voyages out on the Beagle, for looking at the amazing complexity of the living world and thinking about why it looks like that, asking a question to which he found the answer, but which was hiding in plain sight for a long time. But actually, his first love wasn't really it wasn't evolution. That's not where he started. He started with invertebrates. He was terribly keen on invertebrates. And that stayed with him throughout his career. So while he was writing about, the beaks of finches and the Galapagos and all that kind of thing, he had a definite, as soon as he came back, he had this sort of strand that never really left him in his life. He was terribly, terribly keen on earthworms. And the last book he ever wrote was this one. It's called The Formation of Vegetable Mold Through the Action of Worms. And the amazing thing about this book is not just that, he's this incredibly famous scientist. This is a proper rock star of his time, no pun intended. He's looking at the most mundane thing, the thing that everybody else thought was too boring to look at. And he details the great thing about this book is that it doesn't just say, I found out some things about worms. It details exactly how. And you know what? I've no idea how his family didn't kick him out, because basically it seems that he filled his study with little pots of soil and kept worms in all these little pots for years, and watched what the worms did. And then he roped his sons in. You hear that, Horace went off to such and such a house to count the worms in the ground. They all got in on it. And so he spends a lot of time thinking about these worms. And the thing that he saw this is somewhere early in the book, he said, considering their weakness, the work that they have achieved is stupendous. He understood that worms were not just little things wiggling around in the ground, but that they were actually doing something, and they were doing something important. Now, for all his detailed observations of worms, he's not afraid to be judgmental. some point later in the book, he says this. He's commenting, and he says, these worms, however, worked in a careless or slovenly manner. I don't know how you judge, but he was not impressed with these particular worms. But the important point is that as he gets to the end of the book, he says this, that when we behold a wide, turf-covered expanse, we should remember that its smoothness, on which so much of its beauty depends, is mainly due to all the inequalities having been slowly leveled by worms. And what he's looking at is he's looking at the ground, the world we take for granted, and he's saying there is a reason it's like that, right? There is a reason it's not just a big pile of organic rubbish that's been left over by the rest of the world. Something has turned this into the ground we see, and those are worms. And really, he was one of the first people, so that bioturbation, that's the word for this, when worms are sort of moving soil around and processing it. And actually, some of his experiments are still going on today, effectively. He put a layer of a lime mineral, I think, over the fields in his next to his house to see how long it took the worms to move it downwards. And actually, that layer is still there. That experiment is effectively still going on. So the point is that he understood that you need processes to create the world that we see. And this is what the ground is about. So when you look at this picture, you probably see what most people see when they look at this picture. This was taken in, this is the Botswanan side of the Botswana-Namibian border, taken a few weeks ago. And of course you see the elephants. Yay, elephants, right? Everyone loves big, charismatic mammals with big ears. But we almost never look at the ground. And the thing is that once you start seeing this, a lot of paintings that you see, a lot of photographs that you see, the ground is always there, but it's never in the foreground, right? It's always hidden in the back. But actually, this piece of land is very interesting. The reason the elephants are here is not just that they are too hot, which they were, and they've come down to the river to cool off, which they had. It's that they've come here because they want what's in the ground, because what's in the ground is salt. And this is a salt lick. Salt is the only rock that we eat. And so all kinds of animals came down to this place, and they are literally licking the rock because there's something in it that they need. So hiding in plain sight, the ground is doing something. So what's our relationship with the ground then? What is it that we, why should we think about the ground? In all the many, complications of the modern world, why should the ground be important? Well, Mark Twain made one point. He said, by land, they're not making it anymore. It's finite. Whatever the economists all say about growth, we are not growing any more land. And you can't do that without encroaching into the ocean. And as an ocean scientist, I generally don't approve of that. So the point is, land is definitely finite. The surface area of our planet is finite. But we don't understand how much land it takes to sustain our lifestyle, because it's kind of hidden from us, right? The modern world is busy. There's stuff, comes and goes on trucks, and, we don't know where it comes from. And this plot was made a few years ago it was published in the National Food Strategy, actually, and it's a very clever plot. So what you're looking at here is someone's worked out what proportion of the land in Britain is used for lots of different purposes, and then they've kind of replotted it, so they've moved it all around so it's all together. So if you look at the left-hand side first, you can see that a stonking great fraction of the land in this country is used for beef and lamb pastures. Peats down there in the bottom left, cereal, you can see the built environment. Pigs, got half of Northern Ireland. Up there, right in the north, golf courses. Surprisingly large amount of land that we use for golf courses, much bigger than the amount of land we use for orchards. But that's not the whole story. The reason that this was in the National Food Strategy is that to the right here, on the same scale, we've got all the area of land that we need to feed us that is not within the boundaries of our country. So you can see that we are currently using an area that is almost another country over again just to feed ourselves, and we don't see it. And of course, you can see from this that certain things are taking up a lot more land than other things here. If you want to if you want to free up land, stop eating beef. It really is that simple. But of course, this is just food. So this isn't showing the areas that we use for other things, right? The materials that we, that are perhaps in your phone, what your clothes are made of, all of that also takes up a land area, which is not shown on this map. So the first thing is that in a finite world, we should probably know how much land we're actually using and what we're using it for. So the first reason I think the ground matters is because it's finite, because we've got to decide what to do with it. We don't have a choice, right? We have to have an opinion on this. We have to have a relationship with the ground. The second set of things that my sort of provocation as to why we should think about the ground is a set of statistics. And I know statistics sound boring. These are quite striking. There was a paper published very recently that had added up the approximate number of species on Earth where they all were. And the soil, 59% of them are in the soil of the species, right? So not the biomass necessarily, but the species. There is an enormous amount of life in the soil, in the ground. 30%, just over 30% of all of Earth's fresh water is underground. So we've got the ocean, that's fine, that's salty, not much use if you want to drink it. There's lots of fresh water out of the ocean, and most of it is either in glaciers that are frozen solid or in snow somewhere, or it's underneath, liquid in the ground. So basically all the bits of that are solid are in glaciers and ice, and almost all of what's liquid is in the ground. So there's a lot of fresh water there. The ground is acting as storage. And then the third thing is to do with carbon. You know, we hear a lot about carbon these days. It's a sort of buzzword all over the place. But if we take a look about where carbon is in the Earth system, because that's what matters, right? We know the bit of it that's in the atmosphere is causing some problems. There's more of it there than we would like. So then the question is, well, where else could it be, right? Where is the carbon sitting? And where do we have to worry about it coming from and going to? So I'm about to show you a pie chart that shows you where carbon is within the Earth system. So there's actually two circles here. The big white circle that doesn't quite fit on the slide, that represents carbon that's held as inorganic carbon in the ocean. It's kind of locked away by ocean chemistry, but it's held in the ocean. And then everything else that's accessible is in this pie chart in the middle. And you can see DOC is dissolved organic carbon. It's just living and dead stuff in the ocean. But you can see from this that an enormous proportion of the carbon that is knocking around the Earth system is in the ground at different depths. So, deep coal and oil and gas, some of it's soil, some of it's permafrost, but it's in the ground. So what the ground is doing really matters, because that carbon is going to interact with the atmosphere. So what I'm going to do is take a little journey through what the ground is, what it's doing, how it's changing, and the ground genuinely and literally is a huge topic. So I'm going to sort of dot about a bit, but I'm hoping that this will give you a feel for the richness of what there is to know about the ground. So let's start with what the ground is. Now, I'm not a geologist, although I do like rocks. As a kid, I'd have quite liked to have been a geologist, but didn't happen. But when we think about the ground, this is generally, if we think beyond the surface, we think about this, right? Rocks like this. This is the Grand Canyon. It's a particularly beautiful example of what we think about the ground. And the rocks here have a huge range of ages. The oldest rocks in the Grand Canyon at the bottom are 1.8 billion years old. And then there's all these layers on top which tell stories, kind of built up one on top of the other. And then a river has cut through and made the deep canyon here, which has cut its way through all the layers so we can see. So this is what we think. Now, I'm not a geologist, but even here, you can see there's lots of different types of rock. There's lots of different types of stories going on here. And so, yay geology, right? That's the ground. And actually, within Britain, we have an astonishing number of rocks. The British Geological Survey has some lovely online tools where you can play with all of this. So this is a geological map of the United Kingdom. The very all the different colours represent different kinds of rock at the surface. The very oldest rocks are in the top left up there, sort of on the Isle of Lewis, and those are 2.7 billion years old. They are extraordinarily old rock, more than half the age of the Earth. And then they sort of get younger as you come down into the southeast, and the youngest rocks are down here. So there's an enormous amount of variety in what the ground is made of. Even in our very small island, there's an enormous amount of variety. Now, remember this shape, because this is going to come back. There's this kind of curve in the southeast down here. We'll see that pattern again later. But the point is that when we think about the ground and what we can get from it, this tends to be it, right? What can we extract from it? What comes out of it? And of course, in all of these different types of rock, there's lots of different types of atoms. So, you know, this is the, these seven metals here that come not just from these ores, but similar ores. I think iron ore, that mining for iron ore is 93% of all metals mining, and everything else on this comes to about 99% of all metals mining. So we're very specific in what we go after. And of course, having access to all these different types of atom gives us enormous flexibility in what we can make and what we can do. So, you know, the ground's useful for that. But let's come to a different view of Earth, right? All of the sort of geology gives us the idea that the Earth is solid. It's like that bit of the Grand Canyon. You look at it, it's rock, move on. All we need to know is what kind of rock it is. But let's come back to that statistic about fresh water, because where is it, right? I mean, if the rock's solid, and then it's solid, right? Where is all this water sitting? And of course, it's not completely solid. It's full of cracks and fissures. There's space in there. So in this sort of representation here, you can see there's land up here. There's ground, but the ground is made up of rocks with crevices and pores, and they can fill up with water, and so that you get this thing called a water table, which is where the water sits on land. So basically, this is what groundwater is, right? It's water that is down there, hiding in these nooks and crannies, and there's a lot of it. This is a map that was published a couple of years ago, 10 years ago now, and what you can see here is a map of, if imagine you stand on a square meter of the Earth, you collect all the water that's down beneath your feet, and then you pour it into a pool on the surface, and then you can see how deep that pool is. So we can see that in Australia, for example, it might be only 10 centimeters deep, not a lot of water hanging about underground in Australia. But if we move up towards Northern Europe, perhaps Florida, the really dark blues on this map, there's 50 meters worth of water. That's the depth of a sea, right? Hiding underground. There's a lot of water there. And that water is doing things. So this paper is a landmark paper that came out 2.5 years ago now. And it was one of those papers that was just a shock to the system. So what these scientists were doing was looking underground. This work was done in Alberta, in Canada, near the tar sands. So there's lots of sort of fossil fuel deposits in the ground there. So they've got lots of deep holes. And because there's lots of fossil fuel deposits and lots of mining, they keep an eye on what's happening in the groundwater. So they've got all these boreholes. And here's a map of Alberta with all these sort of holes. And that means they can sample water from different depths. So the important thing on this plot here is not exactly where all the boreholes are. It's that it shows water having an age. So what does that mean? A groundwater expert will say that the age of water is the time that has elapsed since it was last in contact with the atmosphere. So if it's in a lake at the surface and it's touching, you know, it's kind of going round and round, it touches the atmosphere every day, it's got no age, right? It's basically being born today, every day. But if you go down into the earth, you start to find water that hasn't seen the surface for perhaps 8,000 or 10,000 years. It's been away from the surface for a very, very, very long time. So they went looking to see, so that's what the colours on here, that younger water means water that's maybe only a few years or tens of years old. The purples on here, the old water, are many thousands of years old. So it's a long time since they've been in touch with the surface. So why does that matter? Well, if we think about what you might expect, close to the surface, that's where all the good stuff is, right? There's sunlight up here, there's photosynthesis, there's light to make oxygen. So up near the surface is where you expect to find oxygen, right? Because that's where it's being made in the sunlight. That's where you expect to find nutrients because they're being formed up near the surface. And you kind of expect that as you go down, you know, they get used up, and then by the time you've gone down into the groundwater a little way down, nothing interesting there, right? Should all be dead. Not what they found. So the first thing is, so this plot here shows the depth of the well. So you can see they started sampling up near the surface, and they went down to around 250 meters deep. So they're going quite a long way down. And then this axis here along the bottom is the amount of dissolved oxygen in the water. So you can see that up near the surface, lots of oxygen, jolly good, that's where we expect oxygen to be. The shocker was this, it's not zero, right? The expectation would be that by the time you're 100 meters down, all oxygen has been used up, right? Loads of organisms really want oxygen to live. They're going to have consumed everything, right? Nothing left. And yet, consistently, this was not zero. So that was a mystery. And they kept looking. So then what they did is they looked in these samples to see how many living cells there were. And it looks like this. So the colors here are the ages. So the numbers up the side go from 10,000 to 10 million. And if we look at the younger ones, you know, somewhere sort of less than 1 million cells per milliliter. So some number, not a lot. Intermediate waters, a few older ones. But when you get to the really old water, the water that is deep, the water that has been away from the surface for 10,000 years, in some cases, there are loads of cells, 10 million per milliliter. Now, that's not a huge amount by the standards of a lake at the surface, but it's a lot if you're 200 meters underground and you haven't touched the air for 200 years. So they started asking, what's going on here, right? What's all this about? And some years earlier, it had been discovered that there was a type of bacteria. So I should say here that we've got two types of microbes in general. There are the anaerobic ones, which don't need oxygen in order to live. And there are the aerobic ones that definitely need oxygen. So in these deep boreholes, there's hydrogen and methane percolating up from underneath. And they're both potentially a source of fuel. So there's a type of bacteria that broke up nitrites, something else you found down there, in order to make oxygen so it could eat the hydrogen and make methane. So these all anaerobic organisms had worked out how to make their own oxygen. I mean, this was a niche thing found years ago. But what these research discovered is that not only is that a very, very common strategy, but they're leaky. So oxygen leaks out of this process, and it then injects oxygen into the groundwater. And that's why, back on this plot, that's why these are not zero. There is oxygen being generated way away from light, no photosynthesis involved. And then when they looked at the genetics of the cells in these boreholes, they found that they were actually quite full of microbes that had to be aerobic. They had no way of living without air, without oxygen, right? So there is an entire ecosystem down in these groundwaters that is generating its own oxygen. Aerobic bacteria and microbes are living quite happily, and this is a really complicated ecosystem. And so, is this common? That's the next question. I mean, it's kind of a weird place in the tar sands of Alberta. So the same authors, a couple of years later, went looking in a few different environments. They went looking in the ocean, they went looking in fossil fuel reservoirs, and in bedrock, and in methane seeps. And you can see there's different symbols here for whether the genetics shows that there are microbes that can only eat oxygen, whether there are oxygen anomalies, and you can see that actually this is not uncommon. And the conclusion that they came to, this is a quote from the end of the paper, is that aquifers and rock fractures may also hold up to 30% of the total microbial biomass on Earth. Now, they haven't looked everywhere, right? This figure is an extrapolation from having done a relatively small number of very thorough studies. But the point is that what this showed everybody is that the deep underground world is not dead. It's got its own ecology. It's running off energy from underneath. And it seems to be getting on quite well without all of us up here. Thank you very much. So there's a lot going on. So, you know, it's definitely not dead, the ground. So let's move on very briefly to soil, because soil gets a lot of attention these days for good reason. It's complicated stuff, right? Soil's become very fashionable in all kinds of ways. So I'm also not going to give a whole lecture on soil because it would go on for a long time. But just very briefly, soil is this amazing mixture of solid plus liquid plus gas plus life, right? It's all of those four things together. It's not just the rock and it's not just the organic material. It's the combination of everything. And so what we can see is the composition of soil here. So if we start over on the left, we can see that almost half of it is minerals. So that means rock, right? Gravel, sand, all that kind of thing. And then about a quarter is air and a quarter is water. So that's your solid liquid gas. And then there's a tiny fraction of it there, which is organic matter. So that's either stuff that is living now or has been living in the past. And so we've got dead stuff over that in the middle, and then that tiny little sliver, that's the living stuff. So that's where Darwin's worms are, and lots of bacteria and algae and fungi and all kinds of things. So the two things that really stand out to me from this plot are, first of all, that there's air, and the air matters. There's actually a word for it, soil gas, which is a lovely term. But of course, soil has a finite volume, right? So when it rains, that rain is going to go into the soil, so some of the gas will come out. So the smell that you smell after rain, I think, is mostly from the surface layers. But the point is, you're smelling what's carrying it is gas that's been flushed out as it rains. And the other thing that stands out to me is that all of this organic matter here, all of this sort of stuff, that's where the carbon is stored. That's what we mean when we say soil stores carbon. We mean the stuff that has been alive or is currently alive, and that's storing carbon. I'm glad I'm not a soil scientist, really. This is incredibly complicated. But there's this interesting sort of philosophical debate, right? And there are papers on this in the literature. So do you look at soil as a solid where all the interesting bits are solid that's got a few holes in it? Or do you look at it as a network of pockets which happen to have these obstacles called, minerals sort of in the way? And just to show you how complicated it all looks, these are CT scans from a recent paper. And this is a little bit of soil that is 1 centimeter thick. And they've put it in a CT scanner, and then they've color-coded the pores, the pore size on the top and the places where air and water are on the bottom. And the thing is that in order to understand soil, this is the level you're looking at, right? So when we go digging, you might just, stick a spade in the soil and sort of dig out some, not really think about it, dig out some stuff. But there is a structure there, and that structure matters. And this is the task of soil science. So I'm not going to go into the depths of soil science, but what I am interested in is what the soil does. What does it do that interacts with the rest of the world? And there is a lovely experiment that you can all do if you have access to a bit of space. I think it popped up in 2017, and it was a farmer in the north who got himself in the press for testing the fertility of his soil by burying cotton underpants. And it wasn't just him. This caught on very, very quickly. And now, if you are interested, you can join in with all kinds of citizen science projects. You can assess soil health with underpants. You can plant your pants. Or you can soil your undies for science. Always a valid endeavor. And the point of all this is that if you take something cotton, right, plain cotton, cotton's an organic material, and you bury it, what should happen is that all the microbes in the soil should get to work on it, right? This is food for them. And if you have healthy soil, they will basically eat your underpants. But if you have the kind of soil which has been degraded, where its organic matter has been lost, where its microbes have been lost, where its fungi is not present, and it's just a pile of minerals with some, phosphate and nitrogen chemicals added for fertilizer, it's not going to happen. And so, you can do this test, and this was actually genuinely published in a letter in Science, so you can see here, these are some underpants that have come out of various fields. On the left-hand side, you can see this is rubbish soil, right? 8 weeks, that's how long you have to leave them for this experiment. So you put them in for 8 weeks. If they basically come out, so you could put them in the washing machine and then wear them, that's not healthy soil, right? We don't like that. It's soil that has lost all of its complexity. Whereas at this end, somewhere down here, you can see the only things that are left are the elastic bits. So the microbes have got to work on all this good food. They've been there, they can process it, they can recycle it, off we go. So the point is that even soil, and I know we hear a lot about soil these days, even soil is not just soil. It's an ecosystem, but more than that, it's kind of the glue that holds the rest of the living world together, right? That's the place where solid and liquid and gas and life all mix. And so don't underestimate your soil, and do go and bury your underpants. That's the message from all of that. So let's get to a few of the things that the ground does. And really, this comes, I'm going to frame this in terms of storage. What does the ground store? And the reason for that is that if the ground is storing something, it can potentially release it into the environment or take more of it back. So what does the ground do? Well, as we've seen with the underpants, it's terribly good at recycling things. And we historically have buried things without really thinking about it, right? You know, waste, bodies, things. We just put them in the ground and expect, without really thinking about it, that they're going to go away. So this is Darwin and his worms, right? That we shouldn't take that process for granted. Whatever's going on is very complicated and valuable, and we should value it as a service, in a way, that the soil is providing to the natural world. But on a bigger scale, the ground is storing carbon, as I said, and there's quite an interesting thing about carbon, because it turns out that it's great to eat things, but there's a very interesting balance when it comes to how much eating is a good thing. So let's take a look at how carbon gets into soil and how it might get out of it. So here we've got a little plot here that shows some ground. We've got a tree and some plants, and I don't know if it's a pigeon or a goose up the top. And you can see that there's carbon dioxide in the atmosphere, and when the plant harvests sunlight, takes that energy, builds itself sugars, it takes up carbon dioxide from the atmosphere and builds it into organic matter. So that gives us plant litter or dead roots or something like that, and that then goes into the ground. And it goes into the ground for some length of time, and then basically one of two things can happen to it. It can shift into a form which is a bit harder for anything to eat, so then it just sits there. Or something can come along and eat it. That thing is going to breathe out carbon dioxide, and the carbon dioxide will eventually find its way out back to the atmosphere. So that's the kind of loop around. So the thing is that this doesn't work if recycling happens instantly. It only works if the recycling process is slow, because if all of this was instant, you wouldn't have any humus or any organic matter in the soil, because as soon as it was put in there, it would come straight back up. So the genius of soil is that it holds it in this intermediate state. And it turns out that that matters for our future. And actually, you can see actually at the top there's this statistic, 20 to 40% of soil organic carbon has a residence life exceeding 100 years. But what that says to me is that 60 to 80% of carbon in the soil is going to last less than 100 years. Soil is turning itself over all the time, but it's not a fixed thing. We can lose it very quickly if we want to. So on the recycling, here we go as a simpler version of that. We take up carbon, it sits down there in the soil, either decomposing slowly or not at all. Sometime later, something comes along and eats it and puts it back up there. But here's the thing. We know that biology cares a lot about temperature. And so things like the microbes down here and the beetles and worms, they are not generating their own body heat. They're very dependent on the temperature in the environment around them. And so if you warm up the soil, they're like, great, they get going faster. They recycle more quickly. And of course, in a warming world, that is potentially a problem. And so there's one of the concerns at the moment is that as the world warms, if this recycling process speeds up, the residence time of carbon in the soil goes down, you're potentially putting more carbon up into the atmosphere. While we're on the topic of carbon, let's have a word about peat. I have a very specific relationship with peat because when I was a child, my mum, who's probably listening, hi mum, she was a member of Friends of the Earth, and we used to go around garden centres occasionally and try and persuade them not to sell peat, compost with peat in it. Now, I'm not going to give my age away, but this was several decades ago, right? And still, peat, compost with peat in it is still on sale, which is ridiculous, and I will explain to you why. So let's get to what peat is. Here's a little picture of peat. It's basically sodden stuff, right? Things grow, sphagnum moss, it's very acidic, it's waterlogged underneath, it doesn't decompose because no recyclers really want to live down there. So it just builds up and builds up really, really slowly. There's a living layer, and then down here there's this waterlogged decomposing layer that if you left it long enough and in the right conditions would eventually become coal. So this is a colossal store of carbon, and it's really important. And so it's really important that it stays in the ground because, that's a lot of carbon, and it's really important that it stays wet. So the first thing is, peat really, I'm an enthusiastic gardener, you don't need peat in your compost, right? Just let it be where it is. It's very happy, leave it there. There are peat-free composts available. But the important thing about this peat is that there's quite a lot of it around. This is a plot made earlier, just last year, actually, in a recent report on climate change impacts on peat. So you can see where the peat is here. There's a lot of it in Scotland, but then these blue areas are national parks, Snowdonia and Dartmoor. So you can see we've got peat bogs, and all of these are huge stores of carbon. All that wet, waterlogged stuff is a really important store of carbon. And what they're concerned about is that in a world with floods and droughts, the conditions will change, and some of that peat, some of the carbon in that peat will get released. And the thing in this paper that they were concerned about is peat drying out, because if it dries out, that waterlogged layer is not waterlogged anymore. Aerobic microbes can get in, decompose it, breathe out, and all the carbon goes back into the atmosphere. So the quality of peat's really important. And so this business of carbon being stored in the ground, this all sounds sort of relatively basic, perhaps, but it's really important because the ground is doing things, but it's doing things that it can stop doing. So it's not even about treating the ground badly. It's about allowing conditions to occur which will just change the way the ground behaves, and that potentially has enormous impacts. So let's talk a bit about something else that's stored in the ground, heat. Now, heat's interesting because when we think of the ground being warmed, we think of the sun warming it, right? If you put your hand on tarmac in the summer, it feels very warm. That's because it's absorbed sunlight. But actually, the important heat, so that the top meter or so of the soil will go up and down in temperature as the seasons go on. But deep down, there is another source of heat, deep inside the earth. And it comes from two sources. One of them is there's just heat left over from when Earth formed, when everything was colossally hot. And the other is the natural radioactive decay of various elements that produces heat, and it kind of keeps that warm. So all of that is in the middle of the Earth. So here's a plot of that. We've got the Earth here. So the inner core, the temperature is on the top axis here. So the inner core of the Earth, right now, if you went enough kilometers down that way, 5,000 degrees Celsius. And then you can see it kind of cools as you get closer to the surface. And then up here where the crust is, it gets cooler much quickly. So the top, couple of kilometers might be, kilometers down might be 1,000 degrees, but then you very, very rapidly cool. And the important bit about this is that gradient towards the end. How deep do you have to dig to get to useful heat? Because that heat is slowly percolating out. It's already there. It's being made anyway. If we want to use it, what do we have to do? And the answer is obviously dig a hole. So lots of holes have been dug. So this is a plot of the temperature with depth at various sites in Scotland. And you can see that there's kind of a line that goes through the middle. If you go down to about 1 kilometre, it's about 40 degrees C. If you keep going down, it gets hotter and hotter. But there is some variation. And this comes back to the geology of Britain that we saw before. So depending on what type of rock it is, what it's sitting on top of, the heat sources from underneath, that heat gradient will vary geographically. And that is really important because if we want to use this heat, and it's coming out anyway, right? You might as well use it. You need to know where to do it. So certain types of heat you can extract, low-level heat you can get from anywhere. But if you want the really good stuff, you've got to pick the right spot. So this is a map that is produced by, and there's an online platform you can go and look at this, the UK geothermal platform, where there's all kinds of fun toys you can go and look at. And what you can see here are maps of where heat is available in the UK. So the top one is heat for easy things, ground source heat pumps and that kind of thing. The bottom one is where you want really, if you want piping hot water to come out to do industrial things with, you want to go down there. So if you can see the bottom map of the UK, Cornwall, around Newcastle and up in Scotland, those are your places where the geothermal gradient is relatively steep. So you don't have to go down very far before you get really, really hot rock. And if it's got hot rock, it'll probably have water in it and you can extract the water. But up here, you can see patterns, right? Well, you can see these patterns in the UK again, where the different types of rock are influencing how much heat comes to the surface. And so that influences how deep a hole you have to dig. So this is really useful, especially in a world where we want to decarbonize our energy supply. Why not take the free energy that's coming from underneath? And actually, there are trials on this in Newcastle where they are sitting on top of a whole load of coal mines from the past. So someone's already dug the holes, and they are now testing geothermal, taking water from those flooded coal mines, because of course, coal mines were continually had the water pumped out of them. When they fell into disuse, the water would just come back in. And so people are experimenting with taking water from those mines and just pumping it up to warm people's houses. And those trials are going on now, but basically it works. It's not hard. Someone's already dug the hole. Hooray. Fringe benefit, silver lining on having lots of coal mines. So heat's a very useful resource. And then the final thing I want to mention in what the ground is doing, which is really important, is it's important for us culturally. Sutton Hoo is a very famous archaeological site in this country. It was an Anglo-Saxon ship burial. And it's got more stuff around it as well, but it was first excavated in the late 1930s, and you can see the image here of the bottom of the ship. So the wood has rotted away, but you can see the shape of the ship. Someone was buried in this, left with grave goods, and then there's other sites around, and you can see some of the things that they've found here, these stunning artifacts at the side. And of course, it's not just Sutton Hoo, right? We know, especially those of us in Britain, this place is full of archaeological sites. It's full of our history, not just our geological history and our natural history, but it's full of the history of who we are, and that matters too, right? The ground is not just an equation. It's not just a number in a table that says we could get this and get that and do this. It's something that means something. It's part of our identity, and that's really important in these debates about what land is and who it's for. Okay, so let's get on to a little bit about how the ground is changing, because it is changing. Some of that change is natural and some of it's not. Oddly enough, the ground is changing shape. You may have seen in the news over the summer this story of work on train tracks being done in Essex, because basically the tracks have buckled, and the reason the tracks have buckled is because they're on clay, which can absorb water when it's wet and give it up when it's dry. And that means the volume of the clay can alter by about 10%. So you've basically got train tracks, it's very important trains stay on the rails, on land which is shrinking and expanding as the weather changes. And there's a recent study here where someone's done a projection of where this kind of thing matters most, and you'll see that those curved bands around the southeast of England have come back. The reason for that is that these are really young. These are some of the youngest rocks in the UK, and they've not solidified into proper mudstone. They're still clay. They're kind of young and malleable. They're still clay which can absorb and give up water, and so this is where shrinking and growing as floods and droughts come along is going to matter. So if you're interested in, potential stability of your house, probably, especially down here in London, good idea to keep an eye on that. The ground might be moving under your feet. And you might wonder how you would know. So actually, there is a brand new satellite that NASA has just put up into orbit, launched in July last year, called, I don't know how they pronounce it, I assume it's NISAR. And this is a synthetic aperture radar satellite, which basically means it sends light effectively down to the ground and measures what comes back, and then it does that every time it goes over the top, and it can detect tiny differences, not in the amount of light for this, but in the phase of the light, where in the wave hits the antenna first. And so this hasn't started producing proper data yet. It is about, I was looking, it's the end of February. They're about to start releasing data. But what this is doing is it's basically continually mapping the surface of the Earth. This is from the same instrument on the shuttle a few years ago. It's mapping the shape of the Earth. Almost, I think it's got a 6-day return time, right? So it can measure differences as small as a few millimeters. And that means that this is capable of watching. You know, I'm really excited when the data for this first comes out, because then we will be able to watch. You know, if there's a flood, we will watch the ground expand. If there's a drought, we will watch it shrink. We will watch earthquakes. And we'll be able to see for the first time how the ground underneath us is shifting, which is really cool. So this is I mean, even images like this are really exciting. You can see that, you know, it's had some color added and a bit of vertical exaggeration, but fundamentally, we will be able to see what the ground is doing better than we've ever seen. So one perhaps unexpected way that the ground is changing is that the things that are living in it are changing. And I'm going to pick one particular example, mostly because it's got a great name, a great informal name. I've never seen this in any scientific paper. And the great informal name is global warming. So you may not know that there are around 3,000 species of earthworms. Not all earthworms are the same. Certainly the composting earthworms that are currently in our house, they're not the happiest worms actually at the moment, but anyway, they're different to these types of worms, and these worms are different to the worms that will be in your garden if you have a garden. So there's lots and lots of different types of earthworms, and earthworms are really important as recyclers. So what's the deal with earthworms? What is global warming? Well, this paper that I'm about to show you, it was a study of North America, and North America during the last ice age in the northern parts was completely covered by glaciers, so the ground was frozen solid. There were no earthworms. And when the ice retreated, the ecosystem kind of adapted itself to not having earthworms. So you have forests that have an enormous amount of leaf litter, just, you know, fallen dead leaves. They're just sitting there kind of piled up. They're really important in that ecosystem, and there are no worms. So they stay there. They get recycled on their own timescales. But the worms are coming. And the worms are coming partly because people are buying plants and introducing soil into places where it wasn't before, and partly because warming in general means that the conditions for earthworms, the line is kind of moving north. So this is a plot of North America, and the important thing, the number here is the proportion of all the species that are alien. So if you have 100 species and 50 of them are not supposed to be there and they're alien invasive species, the number is 50. So you can see here that the yellows, they've mostly got their own earthworms, specifically worms this is. So, you know, Florida, Alabama, they're all right. They're mostly their own worms. But the further north you go, you start to see the really dark blues. And these are places where there are almost all the worms are invasive worms, and that's because there weren't really many worms there before. So the worms are making their way north, and of course, along with this, they are eating the leaf litter. They're recycling all of that carbon. They're breathing it out back into the atmosphere. So you're losing the leaf litter from the forests, and you're also shifting carbon into the atmosphere. And the estimate in this quote from somewhere in this paper, 12 of the 13 most widespread earthworm species are alien, which means that they should be somewhere else. I mean, it sounds very sinister to say, you know, this is not quite the film Alien, but could have more serious consequences. So the point is that this is just worms on one continent. So the ground underneath our feet that is doing things that are invisible to us is changing in ways we can't see, and these ways matter. So they have to not be invisible to us anymore. And of course, we're changing the surface. You know, we build things, we chop trees down, we change our farming practices, we build roads, we drain things. All of this is changing what the ground does. It's not just changing how it looks or what we can use it for, it's changing what it does. And the thing about what it does is what the ground does affects everybody. It's you know, we draw these maps of owned land with sort of lines around boundaries that doesn't really, and of course land ownership is important and useful as a legal tool, But it doesn't really encapsulate the fact that the ground is doing things for all of us. And how do we deal with that? And if we look at, there's a great plot here from Our World in Data that shows how we use our land for food production. So you can see along the top there, that's all the land surface, 29% of the whole, everything that's on Earth. A big chunk of that is called habitable, which means it's not glaciers or barren. And then half, pretty much, of what's left is agriculture, and half is forests and shrublands. So, and then if you look at that, so agriculture is a lot, right, of the total, and of course we need to feed people, right? Food is important, but we do use a lot of land to do it. And then you can see how it breaks down here, that 80% livestock, 16% crops. So it's very, very heavily biased towards animals, but the global calorie supply is almost exactly the opposite way around. Most of our calories come from a relatively small fraction of the land, and a tiny fraction of them come from a very large fraction of the land. So this is relevant if you're deciding how might you think about land. Of course we have to feed ourselves, but it's very difficult to get away from the topic of land to how we feed ourselves without facing up to the fact that some ways of using land benefit far more people than others. So let's get round to the ground and us a little bit. We are extraordinarily good at digging holes, what with one thing and another. This is a mine. So when I talked about metals mining at the start, this is a mine where that kind of thing happens. It's in Utah. It is the largest human-made excavation in the world, 9 kilometers across, 1.2 kilometers deep. And it looks like this. It's got these enormous terraces going down into the ground. So copper comes from here. It has to come from somewhere. There are places that used to be mountains that are now holes because we've taken all that rock. Now, copper is useful stuff, right? We do need materials to live. They've got to come from somewhere. But people are starting to ask a lot of questions, not just about the holes themselves, but about the quality of life of the people who work there. There are some alternatives. Using less is always a good idea, but just to give you a couple of examples of other ideas that won't scale up like that, but are, interesting in their own way. A few years ago, I visited a site in Cornwall that was extracting lithium from groundwater. So deep in the ground, there's groundwater, it's got lithium, they pump it up, they take the lithium out, they put the water back. It's not clear how much that will scale up, but that's quite interesting. And this, this thing I'm standing next to here, I think they had a borehole that was 1 or 2 kilometers deep. That's it, right? That thing goes down 1 kilometer into the earth, and they were pumping water out of it. So potentially a much smaller footprint. And the other thing that's come along, and this is perhaps more useful for recycling and landmines and stuff like this, is there are plants that are really good at concentrating weird metals. And so this is just one paper called a hyperaccumulator, which is a very cool name, and it's accumulating rare earth elements around its cells. There's a picture of a nanoparticle that's in there. And so it seems, again, the questions about how scalable this is are very significant. But, if you've got a landfill and it's got lots of heavy metals in it, maybe you can put some plants on it and get some of the metals back. So there's a whole discussion about how we use land. These 2 books I very highly recommend if you want to know more about the options facing us. And particularly Tom Heap's argument over here is that we can use land for more than one thing at once. And that's really important. We can be clever about how we do it and much more imaginative. So this is a map of public land, publicly owned land in this area of London. That black dot is more or less where Gresham College is. And the purple bits are publicly owned. You can see who owns all the bits here, actually. And my point here, this is another great tool. You can go to an app and play about with this. But my point here is that this, of course, land ownership is important, but our concept of what it means to own land is kind of very narrow. And this seeing land only as the thing you draw these maps on misses an enormous part of what land does. And I think it's important to start thinking about the ground underneath our feet, what it does for us, not digging into it without at least thinking about it, not covering it over without at least thinking about it. You should always ask the question, what is the ground already doing here, before we start to modify it. So I hope that's given you a little bit of food for thought. We're back with the elephants and the ground. And so really the summary of this lecture is that land is three-dimensional. It matters, it has structure, it's active, it's alive, it's very definitely wet, it's connected to the rest of the world, and it is really the ground, not just the soil, the foundation of our biosphere, and we should treat it as such. Thank you.
Well, Helen, thank you very much indeed. You've given us a lot to think about. We've only got just over 5 minutes for questions, but let's crack on.
That's my fault.
No, not at all.
Too long.
But if you'd like to ask a question, I think we'll start from the hall. Anybody like to start us off? Yes, Michelle.
Thank you so much for your lecture. It was fantastic. I just wondered, you were speaking about this experiment in Newcastle, taking the heat out of the earth. Is there any drawbacks to that? Is that heat finite and we would run out if we used it all?
So this is what the study is set up to do. So when I was there a couple of years ago, what they were doing, just as one example, is they were seeing, if you went down this bit of mine here and this bit of mine over here, did this one use up the heat for that one, right? So how much can come out? Because, of course, ground is a very poor conductor of heat. So there's plenty of heat there, but if it doesn't move into those spaces quickly enough, you've got a problem. In principle, there isn't really a downside because the volume, the exact temperature of the Earth doesn't make a huge difference. If you take a lot of heat out of one place, by the time that the effect of that comes to the surface, it will be spread out over a very large area. And it's overwhelmed by, right at the surface, the top meter or two varies enormously in temperature as in the summer it warms up, in the winter it cools down. Below that, heat doesn't percolate. That's why wine caves in France are not that deep, right? It's because it's the same temperature down there, whatever's going on up here. So I have never heard, obviously there are potentially structural downsides if you don't dig your holes properly. But I've never heard anyone present I don't know how much you'd have to scale it up before that becomes a problem, but we are in a country that has a lot of coal mines, a lot of old coal mines. And so at the very least, there's a lot of holes already there that it seems we could use with relatively little impact.
Thank you. Any other questions? Yes, at the back there.
I understand that you were saying that there is water underground, and I know that in Africa they use this water that's underground. They dig boreholes. But in this country, I think it's illegal to do that if you don't have a special license. Does that actually mean that the ground would get waterlogged over a period of time if you don't use that water?
So the first thing is that I'm not a lawyer, so I'm not qualified to comment on the legal aspects of digging boreholes or otherwise. So the problem is actually the opposite. We extract a lot of groundwater in this country because it's there. And one of the things, so there are effectively natural reservoirs underground, and we do extract water from them. And one of the problems with them is that they're invisible. So if we have a succession of dry summers and the level of water in those reservoirs goes down, you can't tell from the surface, but potentially you are using up water that you're not going to get back in a hurry. There's a book by Tim Smedley called The Last Drop that talks a lot about fresh water in the UK and where it comes from, where it goes to. When it rains a lot, which is currently a nice problem to have, even in this grey and wet country, the aquifers do fill up, but after they've filled up, it all just runs off into the rivers. So we know that if you have a rain for a very, very long period of time, the ground does get waterlogged, and then it runs off and it hides in other places. And in fact, where I recently was in Africa, which is on the border between Namibia and Botswana, their water comes from Angola, the Angolan highlands, where it rains for a long, long time. That water gets really, really, really sodden. And actually, the wet season over here, when it floods, is 4 months after the rain over there, because it then all percolates downstream. So that water is moving around all the time. So there are big questions about water management of aquifers that we can't see, and people are monitoring it, but we do use that water in this country. I was told recently by someone who studies aquifers that he thought the UK aquifers were currently generally okay, but I think in the past couple of decades there have been periods where they're quite low. So we have to monitor that resource. But if you fill them too much, it all just runs off to the ocean. So you might get a bit flooded on the way. There's a question about the speed of runoff, because if you've got a nice organic area and everything can soak, there's lots of little holes and porous spaces for it to percolate into, it will go slowly. So you reduce the flooding because that water's got somewhere to be on the way. If you concrete over the ground, you basically make a channel and it will just rush down that channel, sit on the surface, and then you get really catastrophic floods because you've just got a hard surface and it acts like a swimming pool. So actually part of water management is having ground that's got holes and pores and things so it can act as a sponge and take up the water when you need it to and give it back when you need it to.
I think on the legal side, you are allowed to, you have to apply to do so, but you generally are given permission, I think, if you have a small holding to put down a borehole.
There might be some requirements around water testing, perhaps.
Yeah, well,
Scotland,
yes. I think as water is becoming more expensive, more and more people are putting boreholes in. But one last question. Yes, sir. Thank you.
Thank you very much. What would you say is the most precious commodity that we have to be careful on Earth?
On Earth?
Yes.
Or in the ground?
on that is related to humans and humanity and
humanity. That's a list, isn't it? That's like being asked to choose your favorite child. So the problem. Here's my instinctive response to that question is to say that the sort of difficulty with that question is that it comes from the attitude that we can write a list, and actually that's not how Earth works. So I think our problem is that we don't see that it's a system. And it's not possible, really, to say, oh, well, we're going to do a bit better with soil over here, but a bit worse with the ocean over there, right? There isn't this kind of, we can't prioritize the top thing and then it will all be okay. So I think the difficulty, which is something that is very difficult in the modern world, is that it doesn't work to sort of prioritize things like that, right? I mean, if there was one thing, it would be putting carbon dioxide into the atmosphere, right? That is just, but even if we stop doing that, we've still got a biodiversity crisis and we've still got food security crises and there's a whole list, but they're all interlinked. And so I think the biggest difference is the way we talk about the planet and the fact that we need to talk about it the same way we would talk about human body, right? We know that if you are in hospital and there's something wrong, they don't give you a drug that's going to fix your kidney but is probably going to make your feet fall off or something, right? We understand that things we do in one place in the human body probably have an influence on all the other bits. And it's kind of the same with the planet. So we have to think about intervening in the planetary system almost like a surgeon on an operating table, right? You've got to make an intervention that might make things better, but you've got to keep the whole system going while you do it. Right? You can't switch, in the same way you can't switch a human off and switch them back on again while you fix their heart valve. We can't switch the planet off and switch it back on again. So we need to behave like surgeons, and we need to be very careful with what those surgeries are so that they don't cause unintended consequences elsewhere. So I think I would question the need for a list. I think it's more of an attitude.
That's a very interesting answer. Helen, we are, I'm afraid, going to have to come to a close, but thank you very, very much for a fascinating lecture. You've given us a lot to think about. And could I just also say that I'm not at all surprised that Helen has won this award for the communication of science, because I think you've done that superbly this evening. Thank you very, very much indeed. May I also